talked about a number of reactions that happen in the alkyl position of carbonyl compound. And perhaps the most important of those reactions is when the carbonyl compound reacts with itself in a reaction called Aldol condensation. It's perhaps the most important chapter of, well, it's definitely the most important reaction of chapter 18, and perhaps the most important reaction of the second semester. In fact, when I taught the nursing one semester survey organic course for nursing students at the University of Utah, this was the only mechanism that I asked them to reproduce on any of the exams. And there are several variations of the Aldol condensation. Depending on whether the molecule is reacting with another identical carbonyl compound, or whether you're doing a crossed Aldol condensation where one carbonyl compound reacts with a second different carbonyl compound. So the name Aldol suggests that the product has an aldehyde function and a alcohol function. In the same molecule. So the product is referred to as an aldol. And to illustrate it, we'll just take the simplest possible aldehyde that actually has an alkyl position, acetaldehyde or ethanol. And if this is reacted with aqueous sodium hydroxide, we will end up getting a product that has the alcohol function and the aldehyde function in the same molecule. And then if this reaction is heated up, we will actually get product that has a carbon-carbon double bond instead of the alcohol. An alpha beta unsaturated ketone, or an aldehyde in this case. The mechanism for this reaction has 5 steps, 3 steps to get to the initial aldol, and then 2 more steps to get to the alpha beta unsaturated carbonyl compound. And it is an equilibrium. The equilibrium is driven to the right by the special stability of the alpha beta unsaturated carbonyl. This is referred to as a conjugated system. When there are 4 adjacent sp2 hybridized carbons with a p orbital on each of them, that's referred to as a conjugated system. Could be longer than 4. The 2 high orbitals interact. Form a delocalized system extending over all 4 of those atoms. There are 2 hybridized. And this is discussed at length in chapter 14. So we'll be saying a lot more about extended or conjugated pi systems as we move forward in the course. So let's think about what the mechanism for this reaction is likely to be. And you can imagine that the initial reaction is simply for the base to remove one of these hydrogens, form water, and generate an enolate ion. basic conditions. And that makes this atom go planar, so I no longer need to show a dashed wedge or a solid wedge. And we know that this is stabilized by resonance. If we were now to just protonate the oxygen, we would end up having done the keto-phenol isomerism, which is always occurring in aqueous solutions of aldehydes and ketones. If there were a bromine, the pi bond would now attack bromine. If there were an alkyl halide, the pi bond would attack the alkyl halide. And if there were a silicon-chlorine bond, the oxygen negative charge would attack the silicon. But in the absence of any of those, the only electrophile that this is likely to attack is the partially positive charge of another carbonyl compound. And since we only have ethanol in this case, it's going to attack itself. So this will come back in to reform the carbonyl. The pi bond will attack carbonyl carbon of the second molecule and push a pair of electrons on to form an alkoxide. So this is a nucleophilic acyl addition with a nucleophilic attack on the delta plus carbonyl carbon. By the CC5R. Or if you're working with the other resonance structure, the carbon anion. The product of this reaction will have generated a alkoxide and this CH2 group will now be turned to an sp3 hydrolyzed carbon. We're just a proton transfer away from our product. At this point, water will supply that proton and we will protonate the alkoxide ion to generate the aldol. This reaction is readily reversible, and in the presence of aqueous phase, an aldol like this can actually sometimes go back the other way. If we keep the temperature fairly low, it is sometimes possible to isolate the aldol. Entropically, it's not particularly favorable because we've taken two molecules and condensed them into a single molecule. So if we raise the temperature, it would be logical that the equilibrium would return in the left-hand direction. But if we keep the temperature low, it's enthalpically favorable because we've broken a weaker pi bond and replaced it with a new single bond. So we have a new carbon-carbon bond here. And that's what leads to the importance of the aldol condensation. It is a carbon-carbon bond forming reaction. And not only is it a carbon-carbon bond forming reaction, but it often takes two molecules of fairly similar size and puts them together into a single, significantly larger molecule, which makes it a relatively convergent synthesis. It's generally better when you're working with synthetic methodology to take two large fragments and combine them than to gradually add one carbon at a time, which is generally accompanied by a loss of carbon, or bad additive conjugation. So 3 steps to get to the aldol, completely reversible. The electron withdrawing hydroxy group here in the beta position actually makes the CH2 group now slightly more acidic than it was to begin with. So the CH2 group can be deprotonated just as we did the first step. transfers. A deprotonation is step 1, a protonation is step 3, and now another deprotonation is step 4. So that's consistent with a lot of these mechanisms being heavy with proton transfer. Generated an enolate ion. And now the enolate ion can come back in, push the pi bond over from carbonyl carbon to the alpha so that it's between the alpha and the beta carbon, and keep out hydroxide, thus regenerating our base. So we have a loss of a Petri group here, not a great Petri group, right? Hydroxide is not a great Petri group, but in this case it can leave because we're in base. To generate our alpha beta unsaturated product, and I've drawn the E isomer here. The E isomer is more stable. And therefore the more likely to form. You'll notice that the net effect of this is to lose water across the alpha beta carbons. There's a hydrogen from the alpha carbon and a hydroxyl group from the beta carbon, which you'll also notice this is not an E2 elimination. Hydroxide ion leaving in an E2 elimination is very unlikely because it's a 4-liter group. You go through this intermediate secondary enolate. So 5 steps: 3 proton transfers, a nucleophilic attack in step 2, and a loss of hydroxide for the alpha beta saturated carbonyl. And now, of course, since we're losing the elements of water, this is not an entropically favorable or entropically unfavorable reaction anymore, right? This is entropy favored in steps 4 and 5. In this case, we would expect delta S to be positive. In this case, we would expect delta S to be negative. But we would expect delta H to also be negative. And when you have the same sign on delta S as you have on delta H, that is a temperature-dependent reaction. At low temperatures, the delta S term is relatively insignificant, and the delta H term, since this is an altitude favorable and exothermic, will dominate. At high temperatures, the delta S term becomes more important, and so the negative T delta S becomes positive, and that makes the reaction unfavorable. It's just exactly the other way. The driving force for the overall reaction is special stability of the functioning of the saturated carbonyl compound. So when is this synthetically useful? Is it synthetically useful for ketones? Well, yes, sometimes. The problem with ketones is because of steric crowding, the intermediate aldol is almost always unfavorable and therefore not isolable. So the reaction is generally only useful for ketones if one goes all the way to the alpha beta unsaturated compound. So if we were to take a ketone like dimethyl, and you'll notice I've chosen this intentionally so that there's an alpha hydrogen on only one side and no alpha hydrogen on the other side. We would expect the other form of enolate. Readily. No difference yet. Now I'm just going to show this across. should be able to attack carbonyl from another molecule, use the field attack. Probably be better to show it to you over here. See there. As you can see, there's going to be some steric interactions. Two carbon bonds over here. Now we have two bulky groups attached to that. So we're going to have some eclipsing and some Gaussian strain depending on what conformer we're in. Transfer will get us to the Aldol. And then as long as we have another alpha hydrogen, and we do in this case, enolate. And then kick hydroxide out. The alpha beta unsaturated carbonyl. And again, we would expect to get the more stable E isomer with the bulky two butyl groups being kept as far away from each other as possible. The aldol is not stable or isomer for most ketones. Significantly less stable for a ketone material because of both steric crowding and electronic effects. But if we heat it, it is often possible to make alpha beta unsaturated ketones from the Aldol condensation. In this case, just as in the other case, there is only one possible Aldol condensation possible, because we only have one carbonyl compound, and the carbonyl compound we chose in both cases had only one carbon adjacent that had protons on it, so there was only one set of alpha hydrogens that could be removed. Next, we're going to have to consider what happens if there's more